equipment bonding jumper, or EBJ, connects the non-current carrying metal parts of equipment to the equipment grounding conductor, or EG, or other grounding electrodes. Its primary function is to ensure that all exposed metal parts are at the same electrical potential, thereby minimizing the risk of electric shock. An equipment grounding conductor, on the other hand, is a conductor that connects the equipment to the grounding electrode system. Its function is to provide a low-resistance path for fault currents to flow to ground, which protects personnel from electric shock during fault conditions. The fundamental difference between an EBJ and an EGC lies in their function and location. EBJ connect non-current carrying metal parts together, while EGC connect the equipment to the grounding system. EBJ are typically located inside the equipment, whereas EGC run from the equipment to the grounding electrode system. Now, let's address the question of whether metallic conduit can be used as an EGC and whether an EBJ is required inside the conduit when it is used as such. According to the 2005 National Electrical Code, specifically Section 250.118(1) and 250.118(2), metallic conduit is permitted to serve as the EGC for the load side of the service disconnect. However, Section 250.102 D and 250.102 E of the 2005 NEC does not require an equipment bonding jumper to be installed inside the conduit when metallic conduit is used as the EGC. The reason for this is that the conduit itself serves as both the EGC and the EBJ. It provides a low resistance path for fault currents and ensures that all exposed metal parts are at the same electrical potential. To elaborate further, consider the role of each component in ensuring electrical safety. The grounding electrode system provides a reference point for electrical potential connecting to earth. The EGC then connects the equipment back to this grounding electrode system. The EBJ bonds together metallic parts of the equipment and to the EGC to create an electrically continuous path. This electrical continuity ensures that in the event of a fault, a low impedance path is available to facilitate the operation of overcurrent protective devices such as circuit breakers or fuses. When metallic conduit is used as the EGC, it inherently provides this low impedance path and the required electrical continuity. The conduit sections are connected together, usually through threaded connections or approved fittings, creating a continuous metallic raceway. This continuous metallic raceway then serves as the path for fault current, effectively acting as both the EGC and the EBJ. Because the conduit itself fulfills both roles, there is no need to install a separate equipment bonding jumper inside the conduit. However, it is crucial to ensure that the conduit connections are properly made and are mechanically secure to maintain the integrity of the grounding path. Loose or corroded connections can significantly increase the impedance of the ground fault path, which can impede the operation of overcurrent devices and increase the risk of electric shock. Therefore, regular inspection and maintenance of the conduit system are essential to ensure its effectiveness as an EGC. There are instances where supplemental bonding may be required, even when using metallic conduit as the EGC. Firstly, if the conduit system is subject to vibration or physical damage, which could compromise the integrity of the connections, a supplemental bonding jumper may be necessary to ensure a reliable ground fault path. Secondly, in corrosive environments, the conduit connections may be more susceptible to corrosion, which can increase the impedance of the ground fault path. In such cases, a supplemental bonding jumper can provide an additional layer of protection. Thirdly, when dealing with sensitive electronic equipment, a low impedance ground fault path is particularly critical to prevent electromagnetic interference, or EMI, and ensure proper equipment operation. A supplemental bonding jumper can help to minimize impedance and provide a cleaner ground reference. In these situations, it is important to consult with a qualified electrical engineer or inspector to determine the appropriate bonding requirements. Moreover, it is essential to adhere to all applicable codes and standards to ensure electrical safety. In summary, an equipment bonding jumper connects non-current carrying metal parts to the EGC, ensuring all exposed parts are at the same electrical potential, while an equipment grounding conductor connects equipment to the grounding electrode system, providing a low resistance path for fault currents. Metallic conduit can serve as the EGC, and generally a separate EBJ inside the conduit is not required when the conduit is used as the EGC, but proper installation and maintenance are crucial. Always verify local codes and consult with qualified professionals to ensure compliance and safety. It is important to remember that electrical codes and best practices can change over time, so always refer to the latest edition of the National Electrical Code, or NEC, and any applicable local amendments for the most up-to-date requirements. Furthermore, proper grounding and bonding are essential components of a safe electrical system, and it is crucial to understand the principles behind them to ensure the safety of personnel and equipment. Incorrect grounding and bonding can lead to dangerous situations, including electric shock, fire, and equipment damage. Therefore, it is essential to seek the advice of a qualified electrical professional when designing, installing, or maintaining electrical systems. In addition to the points discussed above, it is worth noting that the size of the equipment grounding conductor is typically determined by the size of the overcurrent protective device protecting the circuit. The NEC provides tables that specify the minimum size of the EGC based on the ampere rating of the overcurrent device. It is important to ensure that the EGC is sized appropriately to handle the maximum fault current that could flow in the event of a ground fault. Using an undersized EGC can result in a high impedance ground fault path, which can impede the operation of overcurrent devices and increase the risk of electric shock. Similarly, the size of the equipment bonding jumper is also determined by the size of the circuit conductors. The NEC provides guidelines for sizing EBJ to ensure that they are capable of carrying the maximum fault current that could flow through them. It is important to note that the EBJ must be large enough to handle the available fault current without overheating or melting. In addition to sizing the EGC and EBJ properly, it is also important to ensure that they are properly installed and connected. The EGC must be securely connected to the equipment grounding terminal and to the grounding electrode system. The EBJ must be securely connected to the non-current carrying metal parts of the equipment and to the EGC. Loose or corroded connections can significantly increase the impedance of the ground fault path, which can compromise the effectiveness of the grounding system. Another important consideration is the type of grounding electrode system used. The NEC specifies several acceptable types of grounding electrodes, including ground rods, ground plates, and metal underground water pipes. The grounding electrode system must be properly installed and maintained to ensure that it provides a low impedance connection to earth. It is also important to ensure that the grounding electrode system is protected from physical damage and corrosion. In some cases, it may be necessary to use multiple grounding electrodes to achieve the required grounding resistance. The NEC provides guidelines for determining the number and spacing of grounding electrodes. Proper grounding and bonding are essential for electrical safety. Firstly, it protects personnel from electric shock by providing a low impedance path for fault currents to flow to ground, which trips over current devices and de-energizes the circuit. Secondly, it reduces the risk of fire by preventing the buildup of voltage on non-current carrying metal parts, which could cause sparks and ignite flammable materials. Thirdly, it protects equipment from damage by providing a stable ground reference, which prevents voltage surges and transients from damaging sensitive electronic components. Therefore, it is crucial to understand the principles of grounding and bonding and to follow all applicable codes and standards when designing, installing, or maintaining electrical systems. Seek the advice of a qualified electrical professional when in doubt. It is also worth mentioning the importance of regularly testing the grounding system to ensure that it is functioning properly. Grounding system testing involves measuring the impedance of the ground fault path to verify that it is within acceptable limits. Testing should be performed periodically, especially in environments where the grounding system is exposed to corrosion, vibration, or physical damage. If the testing reveals a high impedance ground fault path, the problem must be corrected immediately to prevent electrical hazards. Proper grounding and bonding are not just about meeting code requirements. They are about protecting people and property from the dangers of electricity. Electricity is a powerful force, and it must be handled with respect. By following the principles of grounding and bonding, we can ensure that electrical systems are safe and reliable. Consider a scenario where a metal enclosure housing electrical equipment is not properly bonded. If a fault occurs inside the equipment, such as a wire coming loose and touching the enclosure could become energized with a dangerous voltage. If someone were to touch the energized enclosure, they could receive a severe electric shock. However, if the enclosure is properly bonded to the equipment grounding conductor, a fault current will flow through the low impedance ground fault path back to the source, causing the overcurrent device to trip and de-energize the circuit. This will prevent the enclosure from becoming energized and protect anyone who might come into contact with it. Similarly, consider a scenario where the grounding electrode system is not properly installed or maintained. If the grounding electrode system has a high impedance, the voltage on the grounded conductor could rise to dangerous levels during a fault. This could damage equipment and increase the risk of electric shock. However, if the grounding electrode system is properly installed and maintained, it will provide a low impedance connection to earth, which will limit the voltage on the grounded conductor and protect equipment and personnel. In addition to protecting against electric shock and equipment damage, proper grounding and bonding can also help to reduce electromagnetic interference. Electromagnetic interference, or EMI, is unwanted electrical noise that can disrupt the operation of electronic equipment. By providing a low impedance ground reference, grounding and bonding can help to minimize EMI and ensure that electronic equipment operates reliably. In conclusion, equipment bonding jumpers and equipment grounding conductors play critical roles in ensuring electrical safety. They provide low impedance paths for fault currents, protect against electric shock and equipment damage, and reduce electromagnetic interference. Metallic conduit can serve as the equipment grounding conductor, and generally, a separate equipment bonding jumper inside the conduit is not required when the conduit is used as the equipment grounding conductor. However, proper installation and maintenance are crucial. Always verify local codes and consult with qualified professionals to ensure compliance and safety. Remember that electrical codes and best practices can change over time, so always refer to the latest edition of the National Electrical Code and any applicable local amendments for the most up-to-date requirements. Electrical safety is everyone's responsibility. By understanding the principles of grounding and bonding and following all applicable codes and standards, we can create safer electrical environments for ourselves and others. Proper training and education are also essential for ensuring electrical safety. Electricians and other electrical workers should receive thorough training on the principles of grounding and bonding, as well as on the safe installation and maintenance of electrical systems. Homeowners and other non-electrical professionals should also be aware of the basic principles of electrical safety and should know how to recognize and avoid electrical hazards. Education and awareness are key to preventing electrical accidents and injuries. Finally, it is important to remember that electrical work can be dangerous. If you are not qualified to perform electrical work, do not attempt it. Always hire a qualified electrician to perform any electrical work in your home or business. A qualified electrician has the training, experience, and knowledge to perform electrical work safely and correctly. It is also important to obtain the necessary permits and inspections for any electrical work that you perform. Permits and inspections ensure that the work is done in accordance with applicable codes and standards and that it is safe for you and your family. Electrical safety is not something to take lightly. By following these guidelines, you can help to ensure that your electrical system is safe and reliable. Firstly, understand the principles of grounding and bonding. Secondly, follow all applicable codes and standards. Thirdly, seek the advice of a qualified electrical professional when in doubt. Fourthly, obtain the necessary permits and inspections for any electrical work. Fifthly, do not attempt electrical work if you are not qualified.